In today's webinar, we're going to take a look at my Advanced Engineering Math ebook. Look, I'm not here to sell you a book. I'm here to sell you an idea. And the idea is Maple should be the tool of first recourse for teaching, learning, and doing mathematics, and in particular for doing the kind of mathematics that shows up in Advanced Engineering Math courses. Maple shouldn't be an add-on after you master by hand manipulative skills. So it should be an integral part of the learning process. How am I going to get that idea across to you? Well, I have a few examples that I've extracted from the ebook, and I hope that these examples will convince you of the validity of this perspective, that it's better with Maple integrated in what you're doing than simply slapped on at the end. The original Addison-Wesley text, 2001 edition. This is what the cover looked like. The ebook is available here from MapleSoft. This is the landing page. There are some of the ancillaries, a student manual, and an instructor manual. There were 7,000 exercises in the book. 1,000 or so had answers in the back. The student manual contains solutions to those 1,000 some odd problems that were in the back, and the instructor manual has solutions for all 7,000 or some odd exercises. Table of contents for the book. There were 9 units. Each unit had chapters. There were 48 chapters. Each chapter had sections, 273 sections. So each section was captured in a Maple worksheet, and those worksheets became the ebook, appropriately massaged. So there are 273 worksheets for the ebook, plus things like a preface and all of the front matter and the back matter that has been also taken care of in the ebook. And this remaining time, I want to see what happens to advanced engineering math when Maple is made the tool of first recourse. So here are some examples I'm going to use to make my point that it's better with Maple. First example, least squares, Rayleigh-Ritz, Galerkin collocation, approximations to the solution of the boundary value problem for ordinary differential equations. This is an actual worksheet. It has not been doctored up. This is what it looks like. These are the sections that appeared in the book. These are the sections that appear in the ebook. Initialization, any packages and preliminaries that we need. The introduction here has got text. This text appeared in the book. It appears in the ebook. It's the description and the exposition that's needed in between the computations. So we have 4 techniques for approximating the solution to this boundary value problem. What we're going to do is put the approximation into the differential equation. You get a residual. If that residual turned out to be 0, then you guessed correctly. If it's not 0, then you want to make it be as close to 0 as you can, and the different ways in which you can make it close to 0 gives rise to these different solution techniques. I pick an example to make things concrete. So here is a specific example, a boundary value problem for which we can obtain an exact solution. Constant coefficients, second order linear, boundary conditions. Okay, so here in Maple, I get the exact solution. Now, since there are 4 techniques, there are some common preliminaries for each of these techniques. First of all, the approximation. This is what we're going to take as the approximation. Now, phi 1 and phi 2 are chosen to be these polynomials. Phi 0 is x. The reason for these choices are that phi 1 and phi 2 go to 0 at the endpoints. X satisfies the conditions at the endpoints. So this approximation with 2 parameters satisfies the boundary conditions. If you plug that into the differential equation, you will get this residual. It's not 0. If it were, hey, we guessed great, but we didn't. So we need to make this as close to 0 as we can, and here are the different ways that we can make that close to 0. Now here are the computations in Maple. You start out with a general cubic. You apply the boundary conditions. You solve for A, and you end up with the choice that we picked, and therefore you have this residual. The least squares technique for making the residual as close to 0 as possible. Just do an L2 norm, make that be 0. So take r, square it, integrate it. This is the integral. This is its value. I'll call it R2. Look at it as a floating point approximation here. Graph shows that there is a minimum. It's a very steep, narrow gorge that you have to traverse to minimize if you were doing it numerically. But we can do this analytically. Normal equations, take derivatives that equal to 0. You would calculate a b and a c. Okay, here's the b, here's the c, here's the numbers as floats. That gives you this y1 as a first approximation. Here it is as a float. Then you graph it to see how you did. This is the least square solution in red. This is the exact solution in black. We didn't do a very good job. We're going to see if the other methods are better and try and get some understanding of why, what's happening here. And this is the value of the norm, L2 norm of the residual. It's rather large. As we examine this least squares technique for what it was we actually did, we are led to a notion that orthogonality is lurking here. Okay, here's the differential equation. L is the differential operator for this differential equation. Here is the linear combination of the basis functions phi k. You apply L to this approximation. You get the residual. Now the L can go past the sum, can go past the constants, and act on these phi k's. For the moment, let's call the result psi k. When we square the residual and integrate, we get a function of the constants, and we saw what it looked like for this particular example. We want to minimize that expression, so we differentiate with respect to the constants, and you can see here what's going to happen. Differentiating r squared, you're going to get 2r dr dck. Now what is dr dck? Dr dck is psi k. So the conditions for minimization are these integrals r against psi k. That's an orthogonality condition. We are making r orthogonal to the psi k's, which are actually L acting on phi k. So the secret here is orthogonality. But what do you make r orthogonal to? If you change what you make R orthogonal to, you get a different method. And that's what distinguishes these uh, uh, phrases that you get in the literature, Galerkin, Rayleigh-Ritz, etc. So what do we make the residual orthogonal to in the Rayleigh-Ritz technique? Well, we make R orthogonal to the actual basis functions phi k, not L on phi k, as in least squares, but directly make residual orthogonal to the phi k's. Okay, so here's the residual, here are the phi k's. So here are the new orthogonality conditions. These integrals, set them equal to 0, solve for the constants b and c. Here are b and c. Here is the Rayleigh-Ritz approximation, and when you draw the graph, you see that that approximation in red is much closer to the exact solution. What happens in the Galerkin technique? What do we make things orthogonal to in Galerkin technique? You pick orthogonal functions. You take functions which themselves are orthogonal. So you have a wide range of choices for what you do here. I've just chosen two trig functions, orthogonal and 0, 1. The orthogonality conditions then are these two integrals. These are the values you need to solve. You obtain a solution for B and C. That gives you a y3, a third approximation. Here's what it looks like in floating point form. You draw a graph, you see how close visually the approximation is to the exact solution. So what's this collocation technique? What do we make the residual orthogonal to in the collocation technique? Well, we make them orthogonal to these delta functions, which means we are simply evaluating the residual at fixed points. Here I've chosen equispace points. Evaluate the function at these 2 points. You have these 2 equations that you want to solve. You solve them for B and C. Here are the B and the C. That gives you a fourth approximation, y4. In floating point form, this is what it looks like, and then you draw a graph, and you see, well, it's not as good as, for example, Galerkin or the Rayleigh-Ritz, maybe better than the least squares technique. So we want to investigate this a little bit further. So we've got these 4 solutions. Let's just compare what we've accomplished. Okay, let's take the L2 norm, the difference between the exact solution and each of our 4 approximate solutions. Those norms turn out to be, or the square of those norms turn out to be these numbers. Big number here, that was least squares. This was Rayleigh-Ritz. This was Galerkin. This is collocation. These 2 are pretty good. These 2 not so good, but collocation better than least squares. Could we improve collocation? We could try taking more points. We'd have a set of overdetermined equations for the B and the C. You can do a least squares solution for B and C and see if you get better values for B and C. That's one thing, but there was a different thought that I had that I'm going to now share with you. So here's what I said to myself. We've got an exact solution for this problem. Is there a way to work backwards from the exact solution to an optimal choice for the 2 collocation points? This is the approximating polynomial. We have an exact solution, L2 norm of the difference. Well, we can compute that. L2 norm difference. So, minimize this difference. that gives you optimal values for B and C. So here are the optimal values for B and C. This would be the optimal collocation approximation if you could pick the points that gave you this expression. So here I'm doing the calculations. You get messy. We minimize. We get these two numbers which I just showed you, and we call them the optimal B and C. If I use those, I get a fifth approximation, and the norm of that difference is this number, and this is that approximation, and this is what it looks like graphically. So, can we work backwards to obtain these two values for the constants B and C by choosing the correct collocation points? And I'll call those the coordinates U and V. So this is what happens when you substitute U and V. You get these two expressions for the residual. Evaluate these two expressions at these optimal B and C values and solve for U and V. And the U and the V that you get are these two, not equally spaced. And what theory lies behind an optimal choice of collocation points is just not carried any further than this, except to show that there is an optimal set of collocation points. This is just a quick look at the method. It's not an in-depth study of the particulars of that method. A second example here, we look at convolution products by the convolution theorem. Now, in this worksheet that you're going to look at now, I have massaged the actual worksheet so that we could get through this more quickly. Your initializations, question, what is the convolution? And I'm going to get at by means of an example. So I have these two functions, f and g. We'll make these assignments on a graph. F is this blue piecewise function. It's an exponential, decaying exponential, which then is cut off and goes to 0. And the g is one arch of a sine curve. Now, convolution, either of these two integrals, f star g, you can either shift in f or shift in g. There's the graph of f, that's this blue part, and f of minus x. So I'm looking at this form of the convolution integral. Now I'm asking myself, what happens when t is 0? When t is 0, I'm looking at f of minus x. Well, f of minus x is mirror image, reflection across the y-axis. So that's this red bit. Now, as t increases in this integral, this red bit's going to be translated to the right. And so this animation shows that happening. Let's slide to the right. Okay, so you can see that red bit sliding to the right. But that's not the only thing that happens in this integral. That red bit multiplies g. So there's the product between this red bit and this black arch. That produces this green curve. And is the area under that green curve that this convolution integral is computing. And so the amount of green is the value of the convolution. So you can see it starts out at 0, it increases, and then it decreases, and goes back to 0. So here is a visual of what the convolution integral accomplishes. Let's compute convolution by the actual integral definition. For functions like sine and cosine, the integral is easy to evaluate, but our example gives rise to integrals that are more difficult. Let's just take this first form of the integral. Here you have the two functions f and g. We try to integrate this. Maple does not come up with an answer. What you really need here is some assumptions on f and g, because look, the integrand is non-zero only when this condition and this condition are met. Otherwise, one of these factors is going to be zero. If you graph this integrand, the product of these two functions, you see that there is a definite bounded domain over which this integrand is non-zero. In fact, there's a better graph of it, of the region. This is xt plane. This is the line x equals t. This is the line x equals t minus 1. Or t equals 1 plus x. Now, this parallelogram corresponds to what's support for this surface. Red stuff is where that integrand is zero. Green stuff is where it's non-zero. So looking at that graph, you see the integral that you are evaluating is an integral in x. So you pick a t and you integrate in x. So you are integrating x from 0 to this line, x equals t, between 0 and 1. So when t is between 0 and 1, the integral is between 0 and t. For t between 1 and pi, the integral is in between these two lines. So it's between this line, which is x equals t minus 1, and this is x equals t. Above pi, and as far as pi plus 1, the integral is from this line to x equals pi. And this line is x equals t minus 1. So you have these integrals to evaluate, giving rise to a piecewise function. That's the convolution. Well, it's difficult to analyze, messy to evaluate. There's got to be a better way to evaluate convolution integrals. And I think the use of the convolution theorem will do it. Convolution theorem says the Laplace transform of a convolution is the product of the Laplace transforms of the factors. So if you invert, you will have the convolution that you're looking for as the inverse Laplace transform of the product of the Laplace transforms of the factors. Does that work? There's transform of f, transform of g. If you invert the product of those two transforms, you get this expression. Here is its graph. It increases, decreases as we suggested. And if you compare these two expressions, you'll discover that they are the same. Here's an example of a periodically driven damped oscillator. Here's the oscillator, governed by this differential equation. Second order linear constant coefficients. Inert boundary conditions. The driving function is the periodic extension of this function g. Here's a picture of g. This is the driving function, the periodic extension of g, so it's a sawtooth. To begin, I'm going to get an exact solution by Laplace transform. I need the transform of the driving function. The driving function is a periodic extension of g. Well, here's a formula for obtaining the transform of this periodic extension. You need only integrate over one period. This is the compensating factor. Laplace transform. Transform the equation with the inert boundary conditions. You need to isolate y. Invert this. Well, these exponentials make inversion difficult. And the way it's typically done is you replace those exponentials with some name, z, and then you do a series expansion in powers of z. So this is what the series expansion looks like. The factors here, 1 over s squared plus 2s plus 10, that's out here. This is the series expansion of what's essentially z minus 1 over z plus 1. Well, I'm taking a partial sum. My partial sum goes out to z to the 6th. Now I want to come back. I want to replace the exponentials back into where the z's are. So now I'm looking at this Laplace transform, which I want to invert. Well, how do you invert this? Well, every term has this same factor in it. In addition, it has powers of the exponential. Second shifting theorem. What do? You invert this function. I call that h of t. And then the inverse transform of this expression is this function shifted times a heavy side. So there is the exact solution. I qualify that by saying it's exact on at least 0 to 20. How do I know that's exact on 0 to 20? Well, just think about what we've done here. We've cut off the series after z to the 6th. And that gives rise to heavy sides shifted, t minus 6 pi. So the next term that I would have gotten if I had added a z to the 7th would be a heavy side of t minus 7 pi. Now, 7 pi is greater than 20. It's greater than 21. And the heavy side is 0 to the left of 7 pi. And all other heavy sides, which I have ignored, are 0 to the left of 21 and hence 0 to the left of 20. So what you see here is exact on 0 to 20. Next, I'm going to try an approximation scheme. I saw this in an old mechanical engineering text that I had picked up from the library. It was about 1936. And I saw this technique, and I at first said, what are these guys doing? And then I tried it, and I discovered, hey, you know what? This really works. It works good. What you do is you expand the driving term in a Fourier series. Well, you can do that by integrating G, because this is a periodic extension, do that. And here are the Fourier coefficients. This is what the coefficients look like if you make a series of them. Here are a couple of partial sums. This picks up the cosine t term. This is the cosine 3t. This is the cosine 5t. And then what I'm going to do is replace f of t by these Fourier series partial sums that approximate f of t. So we can compare. This is a graph of g over 1, f over 1 period. This is the first Fourier series approximation. It's close, but it's not great. You got stuff here and wiggles here. This is 2 terms, or f2, but you still have a little bit of glitch here, and the endpoints are not too good. This is f3. You still have the peak is not quite perfect, and down in the corners at the endpoints, you can see it's a little bit off. But anyway, let's try this. Let's drive the system with each of these 3 approximations. So you have to solve 3 boundary value problems. And these are the graphs of the resulting solutions. And I've graphed the resulting solutions on top of the exact solution. With it 0 to 20, that's exact. Okay, so if you drive it with f1, you can see it's close, but not perfect. If you drive it with f2, the solution is very close. And if you drive it with f3, you can't see the difference. So it turns out that what I thought was just nonsense, if you examine this using operators, norms, the appropriate norms, etc., you realize the convergence is quick. This works. This is a very interesting application of obtaining an approximate solution to an initial value problem. Non-homogeneous one spatial dimension heat equation. A few initializations. And here's the problem that I'm attempting to solve. It comes from the following scenario. This is the wall of a house. My house in Terre Haute, Indiana, back when I lived in Terre Haute. This is the inside, this is the outside, and it's the summertime. I've been away. House inside has gotten warm. Outside, the temperature is cycling up and down because it's summertime. Cools down a little bit at night. Gets warm in the day. I'm taking 70 as my 0 point, 70 degrees Fahrenheit as my 0 point. This is the function of the temperature with respect to time. If it peaks at 30, and it's 100 degrees outside, which is pretty typical. If at night it drops down to 0, that means it's 70 degrees outside, you might get some sleep. So this is the temperature cycle on the outside of the wall. I want to know what's happening inside the wall. And so I say, here's the heat equation. And I come home from being away. I turn on the air conditioner. And I say, instantly, At time 0, this wall is uniformly warm. The inner wall immediately becomes 0. Now I really need a Robin boundary condition there, but let's assume this: the instant I turn on the air conditioner, it blows cold air in that wall, and that wall is 0. And here's the other side of the wall. So this is temperature in a slab, one-dimensional. 0 to pi, that's about 3. Wall with the cladding on the outside and the drywall on the inside, it might be bigger than that because it's the thickness of a stud, which is 3.5 inches. So this is probably a little bit small. But at any rate, I want to find out what's happening inside the wall over time. By way of the solution, let's break it into two parts. One is the concept behind what we're going to do. Here is the boundary value problem. Because the boundary conditions are not homogeneous, the ordinary separation of variables doesn't work. So you write U as a sum, V plus psi. V will be the solution of a homogeneous problem, a problem with homogeneous boundary conditions. And what function psi will do that? Well, this function psi will do that. However, it will shift the inhomogeneity from the boundary conditions over to the differential equation. So now we will have homogeneous boundary conditions. The inhomogeneous term is minus partial respect to t on psi, and the initial configuration is changed to this capital F, which is F minus psi at t0. Now, V will satisfy this equation, and you can write its solution as a Fourier series with time-dependent coefficients. In order to find out these coefficients, you push this through the differential equation, see what's happening. You have to express G in a Fourier series, that's this inhomogeneous term, again with time-dependent coefficients. So here are the integrals that define the Gn. Because you know what G is ultimately, you can calculate the Gn. When you know the Gn, you can then calculate the Bn's, because there'll be a solution of this first order ordinary differential equation. It's not homogeneous. Gn's appear on the right. There is a variation of parameters formula for giving the solution Bn equals. That introduces an arbitrary constant of integration, which you can take to be these numbers. You know what F is, so you can compute these Bn's. Therefore, you can compute the capital Bn's, and therefore you can compute V, and therefore you can compute U. That is the concept. A Maple implementation of this concept constitutes this algorithm. First, we find out what F is. Then we compute the little b's, because from F you get the little bn's. This is what G is. These are the big G sub n's. Therefore, these are the bn's because we have used this variation of parameters solution to the differential equation. That allows us to write down series for, here's the series for V, but I'm just going to take a partial sum, and having V, I can get U. Since we have U, let's draw some pictures. This is a graph of the solution surface U of x and t, and I've drawn it from time 48 to 96, so I'm closer to steady state. And this is an animation of the temperature profiles in the wall. You can see from this surface plot the behavior is not linear. I was expecting that this, let me just play that the temperature profiles in the wall would rise and fall like a straight line going up and down, a tilted line like that, just rising and falling. And I was surprised to find out that that's not the case at all. Temperature profile on the wall is nonlinear. So what we've seen so far is a distillation of the high points of the worksheet of this section. But this derivation is taken from the worksheet, is a full, complete derivation of this algorithm showing where you get the function psi from and how splitting the solution u into two parts, v plus psi, shifts the inhomogeneity from the boundary conditions to the differential equation. Here is the complete derivation of the solution for the coefficients, and here is the corresponding final details of how you would go about computing a solution to this problem. So it's all there, just that in this presentation I pulled out some of the pieces to make it flow a little bit more quickly. A compound plane pendulum is studied in the 9th unit on variational mechanics. So we use the Lagrangian approach to solve this problem. We're going to begin by initializing, and then let's take a look at what the compound plane pendulum looks like. Be useful to have a figure. So compound plane pendulum, two rods, two masses, two bobs. I have a fulcrum up here in a coordinate system with the origin at the bottom. When the pendulum is at equilibrium at rest, the second bob would be down here at the origin. So if this rod is length R1 and this is R2, then this location of the fulcrum would be, or the pivot point would be 0, R1 plus R2. This is an XY coordinate system. Position vectors R1 and R2 are position vectors to the two bobs. So this one has coordinates x1, y1. Using the angle u here and the angle v here, we get that x1, y1 are given by r1 sine u, and y1 is the full distance, r1 plus r2, less this amount, which is r1 cos u. That gives us the height y1. And then for the second bob, you have, with respect to x1, y1, it's x1 plus this distance, and it's the full distance y1 less this amount, which gives you the height y2. Having position vectors, we can get velocities. Then we can get kinetic energies, 1/2 mv squared. You get a total kinetic energy, potential energies, and a total potential energy, and a Lagrangian. Euler-Lagrange equations for this system. Now Maple has this Euler-Lagrange command. We do some operations on what it returns. In particular, it returns equations of motion and any first integrals it can find. And when it finds a first integral, it uses k as the constant of integration. I want to remove those because I just want the two equations of motion, and I've selected them in an order that remains constant whenever I execute this code. So these are the two equations of motion. Well, these are pretty nasty equations to solve. So typically what you do in a textbook is you linearize. The only way with a pencil and paper you can make any progress. And further simplifications would be things like take the masses of the two bobs to be equal and take the two rods that have the same length. So we use M and R for these common numbers. Then the linearization has sine as for a small angle, so sine u is u, and cosine for a small angle is near 1. Derivatives vanish. So this is what it looks like when you linearize. Right? So now these two equations could actually be solved with a pencil and paper. I'm going to make two further simplifications. I'm going to take the common length of the rod to be 1, and I'm going to take the gravitational constant to be 1. Now, physicists in the audience would gonna slap their heads in horror. There's a coordinate system in which that's true, and I only want qualitative information. It just will make drawing graphs a little bit simpler, and rather than drag through something like 9.8, I'm just going to use g equals 1. So now the equations look like this. Okay, and I want to solve these, but I'm going to solve them in Maple. I will use two different sets of boundary conditions. This first set of boundary conditions has the two bobs being moved to the right, but the bottom bob then being moved further to the right. Okay, so essentially they're both to the right, but with the bottom bob a little bit further to the right. This solution has the two bobs displaced in opposite directions. So the upper bob goes to the right, and the lower bob goes to the left of that. Okay, so I'm going to solve the equations. Then there's some sorting and simplifying that has to be done, and I'm going to do the same thing here. Solve the equations and some sorting and simplifying. This is what the solutions look like. Okay, you can see that there is a common frequency. Well, there are two frequencies, two modes of vibration. Cos this and cos this. What does this tell you about the motion? What does it look like? So you clearly want to draw some pictures. All right, so here are the pictures. Angle U. When you move the bobs in the same direction to the right, they oscillate more or less in phase. When you move one to the right and then displace the bottom one to slightly to the left of that, then the motion is in opposition. Okay, so it's nice to have an animation here. So what you get here, let's just I'll set this to run. Then I'm going to run it. Okay, so on the left you see the two bobs moving more or less in phase, and on the right you see the two bobs moving more or less out of phase. So this is what you can extract if you've got a tool like Maple that you can draw some graphs and so forth. But here's something that you can do with a tool like Maple that you can't do with a pencil and paper. You get a numeric solution of the nonlinear equations. Okay? So we make these assumptions that we made before so that we have a basis of comparison. So these would be the nonlinear equations with these constants given values. Remember, these are the linearized equations. So I'm going to just take one of these two cases. This is the first case, the one on the left, where the two bobs move to the right, with the bottom bob moving a little bit further to the right. And I'm going to do a numeric solution, so that's what this dsolve command will do. And what I want to look at is the assumption about that we make in linearization valid? Are there some terms that are small in comparison to terms that are kept? So these are the terms that are neglected. I've drawn that. Look at the scale. These are the terms that are kept. Look at the scale. So casual glance here confirms that those terms that we neglect are indeed small in comparison to the terms that are kept. Here's a graph where both of these are put on the same coordinate system, and this part here is virtually flat in comparison to the scale of the terms that are kept. You can do that with a tool like Maple, but you can't do that if you're just working with a pencil and paper. Final thought here. The solutions of these differential equations, they can be done syntax free. So here is one of the cases, the leftmost case that we considered. This is the initial value problem that we want to solve. If you go here to the context panel and select solve interactively, problem is in place. This one can be solved symbolically. You tell Maple to solve. You can see that in a bigger window. You press this plot button, you get a graph of U. If you select to make a copy of U and change that copy to V, then when you click plot, you get a graph of U and V both. Similarly, for the nonlinear case, select solve interactively. Now this one will solve numerically. You tell Maple, okay, do the numeric solution, draw the graph. Same way you can get the graph of V done numerically. So you don't have to know all of the syntax for solving those differential equations. It can be done point and click.